everyone. This series of videos is going to take you through page 11, which is an exploration of geometric series, which has been misspelled at the top of my header, so please don't judge. In pages 9 and 10, you really were introduced to a couple of kind of big ideas that are going to continue on page 11. So just before we begin page 11 specifically, I'll take a moment to do a quick recap of some important details. First of all, the word series is referring to a sum of a sequence of terms. So just as a reminder, the word series implies we're going to be adding things up. The arithmetic series that we explored on page 9 refers to the fact that we were adding up things that had an arithmetic pattern, something with an initial value and an adder. And today's lesson on page 11 is going to be adding up geometric series, which again implies that we're going to be adding up a sequence of numbers, but this time they're going to have a geometric pattern, some sort of multiplier to them. Another quick vocabulary term just to be aware of is the word sigma, as referring to sigma notation, because you saw that on page 10 of the packet, and that sigma notation is going to be used a few times in this lesson as well. So make sure you go back to page 10 and remind yourself what sigma means, how it's set up, what the little limits on sigma are. The limits are the numbers at the bottom and the top that tell sigma where to start and where to stop, and how to set up its equation in a sort of traditional format. That's pretty much the same as those explicit equations that we were working with earlier in the chapter. So for page 11, we're going to explore how to deal with a geometric series. The geometric series typically has a lot of the same procedures that you would think of for an arithmetic series, but we're going to have to make some necessary adjustments because of the fact that these do not necessarily have a nice, consistent, even spacing. If you watched the series of videos that had the arithmetic series, specifically the formula that we came up with, 1/2 times a sub 1 plus a sub n times, etc., etc., the story of Gauss and how Gauss pictured his series of numbers really kind of set the tone for how we developed the formula that we used for the arithmetic problems. Unfortunately, the geometric problems don't afford us the same luxury. Remember how with Gauss's problem, we could picture the numbers as a ribbon of values that kind of bends back on itself? We don't have that luxury with a question like number 1, because if you have 2 plus 10, and then the ribbon of numbers bends back on itself with 50 and 250, we don't really have any clear relationship in those numbers. That idea of the ribbon bending back on itself doesn't work anymore because 2 plus 250 isn't the same as 10 plus 50, and that Gaussian approach just doesn't work. And that's not to say that there isn't going to be a way to do these problems. It just means that the way we did it with Gauss's problems is not going to work, and we'll need a different strategy. So the biggest thing to kind of be aware of as we start this process is to just recognize that geometric series by nature are going to be different than arithmetic series with a different formula because of the fact that the numbers don't have a cool pattern. They don't have that ribbon effect. Now, the first question in number 1, letter A, wants us to represent this series in sigma notation. That means we're going to use the notation from page 10 that generally has 2 parts to it. The first part is the actual sigma symbol, and the second part is the equation, or the explicit equation expression, I should call it, that refers to the initial value and the multiplier. So we'll start just with the sigma part, because that takes a little bit of getting used to. First, practice drawing a sigma. Sigma kind of looks like a funky letter E, but it's actually a letter S. So if that's confusing, you might want to practice it a little bit. Some people actually find that if they just write a capital letter M and kind of rotate it 90 degrees, that it makes a pretty good sigma. So you'll just have to practice your style and figure out how to make a sigma that looks semi-readable to you. In any case, sigma needs to tell us 2 very specific things about the series that we want to deal with. It needs to tell us at the bottom where we're starting, n equals, and then a number to tell us which term we want to begin with, and then a number at the top to tell sigma where to stop counting. So as I look at the series as it's given to me in question number 1, I see that the first term they're giving me is 2. The second term they're giving me is 10. The third term they're giving me is 50. And the fourth term they're giving me is 250. You'll notice as I did that, I was writing n equals 1, n equals 2, n equals 3, n equals 4. Some people may even recognize that. That's kind of like those little tables that I was making in previous lessons. So you can think of this however you want to, but typically we interpret the first term that we're given in a problem as n equals 1. So that tells sigma, yeah, we're going to start at n equals 1 here. Now the fact that after 250 it just stops, there's a period here that implies I'm not going to keep going, tells me that once I know the first, second, third, and fourth terms, sigma's kind of done. We're not going to keep going past that. So I'm going to put a little 4 at the top of my sigma expression to show that this problem is only concerned from term 1 to term 4, and that's it. After the sigma, we write what would basically be the explicit equation for this geometric sequence. So if we think about the fact that this is a multiplier of 5, that's definitely tipping us off that our problem is going to have a 5 to the power of n. We're pretty used to that idea, that the multiplier is the number that goes in the parentheses to the power of n. But I need an initial value to go in the front. And that's the only part that's a little inconvenient, is because the initial value by definition is the 0 term. And since this series starts by default with the first term, I have to think with a little bit of inference in mind. If the pattern is multiplying 5, then the 0 term, which would have been the term before the first term, means that I would have had to think backwards for a second. And if I think backwards through the pattern, the opposite of multiplying 5 is dividing by 5. So 250 divided by 5 is 50, 50 divided by 5 is 10, 10 divided by 5 is 2, so 2 divided by 5 must be 2/5, and that must have been my initial value. If you prefer to write it as a decimal, 0.4, that's fine as well, so you can kind of leave that in whatever way you feel more comfortable. So there's my sigma notation. Sigma tells me to start at term 1, keep going till term 4, and it's telling me that the equation that generates this pattern is 2/5 initially times 5 to the power of n. Now as a quick check, because sometimes we write a sigma expression but aren't really sure that we're writing it correctly. It's kind of like learning a foreign language for the first time. Sometimes you write a sentence and you don't really know if it's correct or not until you really try it out. Maybe with like somebody who speaks the language, so you can see if they actually understand what you're trying to say. The best way to make sure that this language is understood is to plug in your n values and to verify that they actually are going to work. And the easiest way to do that is twofold. You could do it in your head with mental math, or if you have a calculator, you could do it in a calculator. And I'll show you quickly what that would look like with just actually a couple of examples. If I wanted to plug in and make sure that my sigma starts in the right place, that would mean that I want to plug in and verify that the first term really is going to start me off at 2. I could type 2/5 times 5 to the power of first term, so 1. And my calculator gives me 2. Yep, the first term is 2. So I know that sigma is kick-starting me in the right direction. Now you can check each individual term if you want to. So if I retype and do 5 to the power of 2, yep, there's 10. There's my second term. You could then do 2/5 to the power, 2/5 to the power of 5, or times 5 to the power of 3. That's 50. Yep, that's my third term. And then one more quick check to the power of 4. That's 250. Yep, there's my fourth term. Some people don't show all of the terms, especially in longer sequences. Some people just check the first term and the last term to make sure those are okay, and they assume that the middle is probably fine too. But that's a quick way you can check, just in case you want to test your equation, make any tweaks to the equation, especially if you have the wrong initial value, or maybe your order is off a little bit. You can always do a quick double check to make sure that your equation works. That if you plug in n, it really does give you each of these individual term values. Now in letter B, it says find the sum of the series. Now, I don't know about you, but if I see four numbers and they simply say find the sum, I'm not going to reinvent the wheel. I'm just finding 2 plus 10 plus 50 plus 250, and I have no need to do that in any complicated way. 250 plus 50 is 300, plus 10 is 310, plus 2 is 312. I don't see any reason to make that more complicated than it needs to be. But do a quick preview of the rest of the page. If you look down, for example, at question number 3, you're finding the sum of the first 8 terms. Look at how uncomfortably large some of these numbers are getting. 5, 15, 45, 135. If I extended this pattern to the first 8 terms, I'm going to get some pretty gigantic numbers. I'm definitely going to have to use a calculator. Some of these are fractions, and that's going to get even uglier to try to add. Can you imagine getting common denominators and having to add 1/3 plus 1/9 plus 1/27 plus 181 plus 4 more terms with gigantic denominators that are just going to keep getting bigger? I mean, that's going to get really awkward really quickly. So naturally, while letter B seems like it's easy and I shouldn't need to do anything fancy, I'm starting to kind of think maybe I should have a backup plan. Maybe there should be another way that we can do these so that if the numbers aren't quite as nice as they were in number 1, I still have a way of coping. Fortunately, there is a way to do it, and they're giving it to us in letter C. You may remember when we did the arithmetic problems that we developed our own formula, but it really took an entire playlist of videos, and in some cases, some pretty hefty leaps of logic to get us to a formula that worked. We had to think basically like our own inner Gauss, and we had to come up with a pretty abstract formula out of thin air. This question is giving us a formula to use, which is really nice. Our job is simply to decode the formula and make sure we understand what it means. In this formula, and I'm going to break it down in pieces and kind of color code the pieces, we have a sub 1 times 1 minus r to the power of n all over 1 minus r. So I'm going to highlight a few aspects of this according to what they say in letter C, and hopefully you can kind of follow where I'm getting some of these details from. The first thing I'm noticing is that it says a sub 1. A sub 1, it says, is the series first term. So we know, typically, that the first term is where n equals 1. So I'm looking at this problem. I'm seeing the first term, that's 2. So naturally, I'm just thinking, oh, first term, that's where n equals 1. Okay, I can substitute a 2 into the formula in that spot. So I'm just going to do kind of a quick replacement so I can see how all the numbers shake out. Now, my parentheses 1 minus, it says R is the series multiplier. So again, I'm going back to vocabulary I've already heard. I know that this series has a multiplier of 5. I already figured that out when I did my sigma notation. Sorry, I just made that really dark there, but hopefully you can still tell there's a 5 under there. So if I know that the multiplier is 5, then that means R, I'm regretting this choice of blue, so bear with me here. Hopefully we can still see it clearly enough once I darken it a bit. Hopefully that's not bad. That R is the 5 to which I was referring as the multiplier. Now it's going to appear twice in the formula. Once in the parentheses at the top and again at the bottom. So I'm going to make those 2 substitutions there just so you can see where I've gotten it from, but hopefully you can tell R is an identifiable quantity. That's something we've already seen. That's something that we already identified. We know that R is 5. We're not reinventing the wheel here. Now the last thing that they told me is n, and there's nothing in part C that defines what n is, so I just need to remember I've been using n all along. In this case, or in this context, n is the number of terms we're adding up. So that might not have necessarily been the interpretation of n that you were thinking of, but hopefully that's something pretty straightforward. That if you looked at this problem, we are adding 1, 2, 3, 4 terms together. So n in this context would be 4. Just as kind of an example here for this specific problem, n would be 4 because we're adding up 4 terms. So just to kind of recap the three really big parts of this thing here, a sub 1 is the series first term. N is the number of terms that we're adding up. So again, I'll just kind of highlight so that we can break down these main parameters here. And apologies that the camera makes all of these highlighters show up really dark, but hopefully you can see it. N is the number of terms we're adding up, and R is the multiplier. So, by substitution, a sub 1 is the first term, that's 2 in this example. Parentheses 1 minus R, that's 5 in this example, the multiplier. To the power of N, that's 4 in this example, because there are 1, 2, 3, 4 terms, over 1 minus R again. So that's the same R. Now, if I clean this up a little bit, I might want to use a calculator for some of this, but 1 minus 5 to the 4th is 1 minus 625, all over 1 minus 5, which is negative 4. If I do that subtraction, 1 minus 625 is negative 624, divided by negative 4. So I'm just kind of treating this as if it's basically just a regular old problem to do. And to play it safe, I'll use a calculator just so I can use a bit more consistency. I have 2 times negative 624 divided by negative 4, and I get 312, which seems familiar because that is exactly what I got when I added the numbers in a very straightforward way. So you can tell that while this formula might seem convoluted, it gives us another way of getting the sum. And this will probably come in handy when I have to start adding really big series of numbers or values that start to get really clunky to calculate. Like if I had to keep extending this series, 250 times 5 is going to get pretty big. That answer times 5 is going to get really big. And that answer times 5 is going to get really big. So you can tell that having the formula as a backup plan is going to be a nice option. Because if the numbers start to get really big, I don't want to have to keep extending the sequence and using a bunch of scratch space just to figure out the numbers. And then on top of that, have to finally add them up. Oy. It seems easier now to have a formula where all this information is pretty readily accessible. In fact, challenge yourself for a second. Try question letter D. It says, extend the original series by 5 additional terms, then find the sum of the series. I'm going to challenge you to do this one of 2 ways. The first way is to actually extend the series. Find the next 5 terms and add them all up. The second way, which I might recommend as kind of the way you might want to try it, is to use the formula. If we extend the series, what would a sub 1 be? What would R be? What would N be? And which way is actually easier, more efficient, or just personally more appealing to you? In the time between ending this video and beginning the next one, I'm going to ask you to try question letter D on your own to see which way occurs to you. If you're not really sure, then I'll walk you through the steps in the next video. But for now, take this opportunity to think for yourself a bit. Which way do you think you could see yourself using this formula or the extension strategy? And which one seems more practical? Good food for thought.